Stepwise, and it's a platform that I think can be a little bit intimidating when you're just starting to use it. And so hopefully what you see today helps you understand a little bit about what's going on behind the scenes with Stepwise and lets you use it more effectively. So what we're going to cover today is really just, what is stepwise regression? I'll argue and show that if you've built any sort of linear model in JMP, you've probably done some form of stepwise regression. It might not have been through the platform, you might have been doing it manually. And so stepwise regression is really just an algorithm to help you build those linear models with some stopping conditions, with some way to figure out what the most appropriate model might be for your system. We'll do a bit of a deep dive into the platform here. There's a lot of controls, there's a lot of options. So I'd like to demystify those a little bit. There's a lot to cover, so we're not going to cover everything today, but I'll at least show where you can go to get some additional help as well. So I'm not going to go through the basics of linear regression today. I'm going to jump into some fit model reports with linear regression. If you need a refresher, there is a really good mastering session on fitting and specifying models that would help, as well as the STIPS module on regression is really excellent. So both of those, if you do need a refresher on least squares regression, those would be good resources. And then finally, we'll talk about some examples. But we will set this up with a few slides and just a definition. It's very simple. So stepwise regression is really just a method for selecting a subset of model effects in a linear regression model. You might ask, why don't we just use all the variables? If I've got all these variables in a process, why don't I use all of them? Well, in a lot of cases, models with fewer parameters are going to be easier to interpret or explain. If you've got 100 variables in your model, it might not be all that straightforward to explain it or interpret it or deploy it. Generally, when you reduce the number of variables, you'll find that you can take out variables without affecting the model, without affecting the prediction capability. And that makes those models more generalizable, and you're going to avoid overfitting that data. And in some cases, stepwise is necessary. You might not have enough observations in your data set to do a full least squares regression model. Remember, if you build a least squares regression model, you have to have at least one observation for every model term. So if you have a wide data set where you've got more variables than you have observations, you have to have some form of variable selection. And ultimately, all of these are going to strike this balance between simplicity or effect sparsity, parsimony, however you want to talk about that, and then that model accuracy or precision. So stepwise regression helps us find that balance. We're going to frame the story today with this production problem. And if you've seen, I gave a mastering session last year on identifying important variables. So this might look familiar if you attended that. I'm going to use the same data set or a subset of that data set. But in this problem, we've got some manufacturing process that gives us some consistent yield. Our process, of course, bounces around that. But at some point it went much lower. And maybe this scenario, we've got root cause analysis. And so we've got this highly integrated complex manufacturing process, and we want to figure out if we can relate some of those process variables to the point where we get this low yield. And so, in this scenario, we've pulled in all this data, we've cleaned it up. Maybe we've already done some pre-processing of the data, and we're ready to start analyzing it. And so the goals that I want to hopefully accomplish today with this presentation is we're going to use stepwise regression to find those important variables. We're going to use different stepwise methods, and then we'll show some ways to evaluate those models. Second, I want to use stepwise regression to build a model with higher order terms. So sometimes if you've got complex processes, it's not going to be just a main effects model. You might have interactions, you might have higher order terms. And so how do we take the results of some variable selection process and translate that into a model that has these more complex terms? And then finally, I want to show how JMP Pro can help streamline stepwise regression methods to build even more robust linear models. So if you are building linear models and and you're making decisions based on those, and you're using data that might be from historical sources or experiments that aren't designed statistically, then I think you know you'll benefit from seeing GenReg, the generalized regression platform, and how it can really be. I think one of my colleagues described it as a one-stop shopping for linear models, and we'll talk about what I mean with that as we go on a little bit later. All right, so stepwise regression. Before we get into the stepwise platform, I just want to show how you can. We'll go through the different methods here, but if you have built a linear model, you have probably built you have done stepwise regression, but it might have been manually. So I'm just going to go over to our data set. So in this data set, I've got 100 variables, and I've grouped them all up as these columns. We've got all continuous variables except for 2 categoricals. And then we've got a validation column here that we'll use later on when we get to GenReg. And we've got our yield, which is our response. And so if we went in, we've got 100 columns, 100 variables, and we've got 560 observations. So we could build a least squares model. So I go to Analyze, and we want to go to Fit Model, and I want to put in yield, and then all of my variables. And I'm just going to do a standard least squares model and click Run. And what we get is an actual by predicted plot that has an R squared of 0.8, so we might be excited about that. But then we look through our effects summary, and we just see all sorts of variables here, and a lot of them have p-values that might imply that they're not important in this process, that we could ignore them. And so if you got this sort of model output, you might have then selected one of these terms or maybe a block of these terms and started removing them. If you've ever done this while you've built a linear model, then you've done stepwise regression. And this is a fair way to do it. And you can inspect these p-values and just continue trimming out these model terms until you get to the point where you're satisfied with that model. The problem with this process is it's quite manual. You don't get any feedback on how well that model is improving over time. You just have some summary statistics here. And depending on the complexity of your system, you might be inadvertently removing terms that might have been important if you had removed terms in a different order. So there's some drawbacks here, but this is a very common thing to do. And you get to a reduced variable set, and you can go and then look at the profile or evaluate this model many different ways. So if you've built a model this way, then you've done stepwise regression. But the stepwise regression process really just formalizes this into some algorithms that help you build that more effectively. There's a few methods that we're going to talk about today. So there's backward elimination. Backward elimination is where you start with all the model terms. So you start with that full least squares model and then remove one model term at a time. And the model term that you're removing has been evaluated to be the least important model term in that model. The opposite of that is forward selection. So in this case, you start with no terms in your model, and then you find the best one that's going to improve your model, add it, reevaluate it, and continue that process. And then you can have a mixed method where you've got rules in place to either add or remove a model term as you go through the algorithm. And so you can think of this as just a cycle. So you're going to start with that baseline model, and you're going to evaluate all the next possible steps. So if you've got 100 variables, you've evaluated all 100 variables and figured out which step, either adding or taking out a model term, is going to improve the model the best. So you find out what it is, and then the algorithm will put that model term or take it out of the model. And then you're going to evaluate that new model with respect to some stopping criteria, some stopping rule. And so that stopping rule is going to help inform the algorithm on when to stop. And I just want to take 1 second here just to show why we can't use a summary statistic like R squared. So if we want the best model, maybe we just want the highest R squared. But the whole point of this is to reduce the number of variables. So we need to have something else to help us evaluate whether or not we need to stop this algorithm. And we're going to use something called information criteria, specifically the AICC or the BIC. You don't have to know the math behind these in order to use them, but just know that they're a way to help you evaluate the fit of a model. And so if we just used R squared, and this is results from Stepwise that we'll do in a little while, but we can plot the R squared of the model versus the number of parameters that we're putting in that model. So down here, when we only have a few parameters, we're going to have a low R squared. And then as we add more and more parameters, our R squared is going to go up and it's going to start tapering off. So by this point, when we get over to 30 or 40 parameters, every model term that we're adding is not adding a lot of R squared. It's not explaining a lot more variance. And so, just eyeballing this, you might say, well, maybe, somewhere around here is where we would stop, where every model term we're adding is not getting us a lot of gain in terms of R squared. And that's what the AICC and the BIC try to help you do. And these are different calculations. And if you're interested in understanding more about the math here, you can go to the documentation and they describe, the calculations behind it. But you don't have to understand that to understand what they're doing. So in this case, across the same x-axis, now we've plotted the AICC and the BIC. And so in this case, our AICC is starting off high, and every model term that we add is dropping that down lower and lower. And in the case of the BIC, it hits a minimum value, somewhere, in the low 30s of parameters, and then it starts to increase again. And so for the AICC, it's a little bit more forgiving. It will let you put in a few more model terms, and so it looks like its minimum value is here around 40 or 50, 45 or 50 model terms. And the goal here is to say, okay, well, these minimum values, that minimum BIC or minimum AICC, is really finding that balance between the ability for the model to predict the response and just having too many terms in the model. And so Stepwise uses these information criteria to help figure out when to stop this algorithm. And so when we'll evaluate that model with respect to that stopping rule and then determine if that stopping rule was achieved. If it wasn't achieved, then that new model now becomes our baseline, and we go through the cycle again, and we'll just keep going through this cycle until at some point one of those minima are achieved, and then we say, okay, that's the model that we're going to be satisfied with. That's going to stop the algorithm, and then we can start evaluating it. Let's get into the Stepwise platform and show how we can start building these models. So to launch the Stepwise platform, we're going to go to Analyze, Fit Model, and we're going to cast our yield as the Y, and then all of our variables as the model effects. Under personality, though, this is where we make a change. Instead of going to standard least squares, we're just going to go to stepwise regression. And then we'll click Run. And so we've got this intermediate step now. So this is the platform where we're going to specify some of the rules that control the algorithm. And so the first rule that we want to adjust is a stopping criteria, or the stopping rule. And so under this drop down here, we can specify whether or not we're going to use that BIC, so that it penalizes that the number of model terms a little more harshly, so you'll have fewer model terms, or the AICC, which will allow you to have a few more, or you can use something called the p-value threshold. We're not going to talk about this method today, but the documentation is a great place to go to learn when and why you might use that. Now next we're going to specify the direction. So we've got forward, backward, and mixed. So like we had talked about before, so these are going to start with the different baseline models. Forward starts with 0 terms in the model, backward starts with all of the terms, and mixed starts, well, I think you can start it either way, but it will it will add or subtract model terms depending on the rules that are in place. And then finally, there's these rules, and I will admit, when JMP users have talked to me about getting into Stepwise, this is probably one of the more confusing parameters. And we're not going to go into a lot of the um, uh, details behind this stopping rule, but it shows up when you have hierarchical terms. So hierarchical terms can be like multi-level categoricals or interactions. And so there's a number of different rules that you can apply. And if you aren't sure which rule to apply, you can go to the documentation to figure out what might be most appropriate for your system, or you can use what I like is the question mark up here on the toolbar. So this actually has a really good explanation. If you hover over that with the control or with the question mark, you're going to go right to a shortcut that shows this control panel, and you can scroll down and start learning about those different rules to see which ones might be most appropriate for your system. Um, to keep things simple, we're going to stick with Whole effects. And if you were listening before we started today, Gail was asking if anything in Stepwise is different between 17 and 18. And this is the one thing that I've noticed. In 17, you only had 4 rules. Now in Jump 18, you have this fifth rule, which is Whole effects respecting heredity. And this actually is quite helpful. And so it helps you interpret those interactions a little more cleanly, especially when it comes to the prediction profiler later. So this is the one we're going to select today. Of course, you could select any of those depending on your data set and the models that you want to build. Okay, so we've got the rule, the direction, the algorithm. The last thing to talk through are just the controls. And so we have some buttons here. So these control whether the algorithm, you start it, you stop it, or you step through it one at a time. We also have some other controls here that help us kick off the model by either entering all the terms or removing all the terms. So you want to enter all the terms if you're going to do backwards regression, and you want to remove all those terms if you're going to do forward regression. And so let's do an example. So let's do forward selection to start. So a forward selection model means that our baseline model has no model terms in it, and that's where we start when you launch this platform. So we can see by our current estimate report that we don't have any models in this term. If we enter a model, we would put a check mark here. And so when you launch this, all of those will be empty to start. And then here we have a report on our model, which in this case only has the intercept and no R-squared value. For now, we're going to hide this, and we're also going to take a look at this step history. So this shows what happens with every step in the stepwise regression. I want to minimize this, and what we're going to do is also just show what this criterion history is. So this is a nice little visual to show what happens during each step of the regression. And if this isn't, it's not on by default. So to turn it on, you can go to the red triangle, and you want to check mark this plot criterion history. And so if we're all set up, so we have nothing in our baseline model, and we want to do forward selection, so we can just click go. And what we can see is we're plotting those BIC and the AICC over time. And we can see that the model is stopped. It went out a little bit further and then found that there was a minimum. If we zoom in on that, we can see that that red X is the minimum BIC value that was found, and it's right here around 35 model terms or so. So we took those 100, we loaded those into the platform, and this is saying, that balance between prediction ability and complexity is around this 35. We can reset this and do AICC and just to see it. BIC versus AICC, these can be your personal preference, whether or not you want to add more or fewer terms at the end of it. And so let's run it again now with the minimum AICC. So I want to switch that to minimum AICC. I want to keep this at forward. But if we look back at our current estimates, we've entered all those model terms. And so we need to clear all those out. So I'm just going to click the remove all button. That removes all the model terms, resets our baseline model. And then what I want to do to clear this graph out is just go to the red triangle, and I'm going to say clear history. And so now we can do this regression again with minimum AICC, click go, and we can see that that continues to go down further than our BIC model and stops here around 48 parameters. And so that's really all stepwise regression is figuring out some balance between the model fit and the number of parameters in the model. And you can choose either of those. Sometimes you might choose both and then make sure that they converge at the same point. And then maybe we'll do one example of a backwards regression as well before we start digging into one of these models. So in backwards elimination, let's reset our history. So we're going to go to red triangle and we're going to say clear the history. And in order to do backwards, remember now we have to load up our baseline model with all the model terms. So we have to start with that standard least squares model. And so we're going to click the button here that says enter all. If I forgot to do that, and maybe I was in this baseline model where I don't have any model terms and I want to do backwards elimination and I click go, nothing happens. It can't go because there's no model terms to take out. So we need to enter all those model terms. And so now every model term is in there. And what we have now is that R squared of 0.8. And I don't know if you remembered, but when we did that least squares model at the very beginning, this is the summary statistics for that least squares model. So every model term is in this model. And now we want to find the worst effect and take it out in a stepwise way. So let's close this down. And you can see our starting point now is over here on the right-hand side because we've got all those model terms in here. And we're going to click go. And so now instead of going to the right, we're going to the left. And we're going to find the minimum AIC value, which was here. And if we had selected minimum BIC, clearly we would have kept going and it would have gone something, like that. And so that's all there is to running the algorithm. It's just knowing, the buttons that you need to push to set that baseline model. And so if we're satisfied with this model, let's say that we're happy with where we ended up in this AICC backwards regression model. Now we can start taking a look at some of the estimates and the step history. So the step history shows us what happened at each step in the regression. So in step one, so in here, we entered all those. The next step, we removed this parameter and then removed that one. And that occurred until we got to some stopping point where it went back and it went back to that best model. And by default, the best model will be selected. You can select any of these models to send over to the fit model platform just by selecting the radio button here. So if you wanted this model for some reason, you would just select it. But by default, the best model will be selected. And then to run that model, we're just going to go to these buttons here. If you click make model, it just takes it to the fit model platform preloaded with all those model effects. And if you click run model, it just goes right to the report. So we're going to do this, run model. And that takes you to the fit model report where you can then, open up your actual by predicted, and you can, look at your, all of your various summary statistics and model fit, and things like that. Yep, so that's all there is to building these models. And if you wanted to start comparing this to other models, then you might need to go to the red triangle, save those columns, save the prediction formulas to the table, and you could stack them up in a profiler. Or you could say, no, this is too many terms. I don't, even though we ran stepwise, I still have too many terms. So then you can just go, the stepwise platform stays open, and you could just go and go back to your step history and maybe select a different model and run that one, or run a different algorithm. So you can keep the stepwise window up and just continue generating different models to see which one might be the best representation of your data. All right. So a lot of the times when you find these important variables, you might be done. Maybe you only end up with a few, or you want to, or that was enough for this. You just want to explain what those main variables are. In other cases, you might want to come up with a more predictive model. You might want to start building in some um, interactions or higher order terms.